Swayam Prabha. Digital India. Educated India.
Till now we have been discussing the vibration problems involving systems which could be described with only one coordinate, that means which possess single degree of freedom. However, we encounter a large number of situations where the number of independent coordinates required to describe the system's configuration is more than one. So therefore, it is necessary to discuss the problems where systems have more than a single degree of freedom. In this direction, we will encounter some new concepts which were not present in single degree freedom systems. So before we take up discussions in details, first let me present certain basic ideas about these new concepts which will be involved in case of vibration of systems with more than one degree of freedom. So we start with the simplest next possible case, that means vibration of systems with 2 degrees of freedom. Of course, we should also keep in mind that we are discussing undamped vibration. As just now mentioned, that these systems will require 2 independent coordinates to describe the system's configuration. It can be in many ways. Maybe it can be in the form of 2 blocks having vibration. So as can be seen easily that this system requires 2 independent quantities x1 and x2 as the displacement of the 2 masses from their respective equilibrium position. Similarly, in case of angular motion, we can have a double pendulum. This is another case of 2 degree freedom. As you can see, the displacements from the equilibrium position, they are represented by two angular rotations of the two rods of length L1 and L2. The displacement coordinates are theta 1 and theta 2. Sometimes the system with a 2 degree freedom system may not involve more than one lumped body. For example, if you take a system with a single body M, so let us consider this body supported by 3 springs, mass of the body is m, and let the body be confined to the plane of the board. So in that case, again the complete description of the location of this mass will require 2 coordinates x and y, and therefore again the system will have 2 degrees of freedom. Similarly, in engineering we encounter situations where a body is resiliently supported. So in this case, the body's motion again, it is confined to the plane of the blackboard. Maybe body is, this center of mass of the body can have only vertical motion, but again it can have a tilt. So x and theta will be the 2 coordinates. Here x and y were the 2 coordinates. Here theta 1 and theta 2 are the 2 coordinates required. Here x1 and x2 are the 2 coordinates. So these are some examples of 2 degree of freedom system. Now there are some fundamental points let us understand at the beginning. One thing that we are considering undamped system to begin with, and I will refer to the situation when damping exists briefly after we discuss this. Now one thing we have seen in a single degree freedom system, if we disturb the system from its equilibrium position, it executes simple harmonic motion invariably without any problem. In case of 2 degree freedom system, suppose this one, I disturb somehow, will the bodies execute simple harmonic motion? The answer is no. That is a very fundamental difference with the single degree freedom system. That means the oscillation, free oscillation of this will not be necessarily a simple harmonic motion if the displacement is given in an arbitrary manner. On the other hand, it is possible to give the initial conditions to start the motion of a 2 degree freedom system in such a way that both the bodies will execute simple harmonic motion, and we will see in the case when one body is executing simple harmonic motion, both the bodies are executing simple harmonic motion, the frequency of that oscillation for both the bodies are same. Phase difference can be there, that means they can be either in phase or out of phase, as we will see later, but the frequency of oscillations will be same and both will execute simple harmonic motion only for some specific cases where the initial conditions are adjusted properly. So therefore, there is a special situation which exists in cases where more than 1 degree of freedom exists, that the vibration is not necessarily simple harmonic if it is disturbed from the equilibrium position in an arbitrary manner. On the other hand, just now as I mentioned, if we disturb it in a particular way satisfying certain conditions, then the system will execute simple harmonic motion, both the bodies, with the same frequency. Now this type of motion, that means where the system is executing simple harmonic motion with the same frequency, all the parts of the body, they are called either natural mode of vibration or normal mode of vibration. Both terms are used. So, this type of vibration where the whole system executes simple harmonic motion with the same frequency, that particular type of vibration is called natural mode vibration or normal mode vibration, and the corresponding frequencies are called natural frequencies. Next question will be that how many such natural mode vibrations will exist and how many corresponding natural frequencies will exist. Now that will be exactly equal to the number of degrees freedom. So natural frequency omega n will have the number of natural frequency will be the number of degrees of freedom. So in this case, when you are considering 2 degree of freedom system, we will have 2 natural frequencies and 2 natural modes of vibration. Now let us start investigating one 2 degree freedom system of this lump parameter type. We need not put the other spring, this is also a 2 degree freedom system, and really speaking we have not lost much in the generality of the case. If we want, we can put, only it will complicate the expressions more, which we need not all the time bother about. So this is a 2 degree of freedom system, and the equations of motion you can write down. So this body in a displaced condition will be here, this will be here, the forces on this, there will be only one force, here there will be a force in this direction with the same magnitude, and these are the free body diagrams, and so the corresponding equations will be and reorganizing little bit, it will be M1 Now from this we can see we can express x2 in terms of x1 and x12 dot. So let us write x2 in terms of x1, because this is a case of simultaneous differential equations with two unknowns or two variables, and let us put it in a solvable manner by eliminating 1. So x2, if we write in this, it will be m1 so x2 is this much, and x2 2 dot will be then obviously now if you substitute x2 and x2 dot in this equation, say this equation. So then what we will get finally, so you can see now actually it is fourth order equation next one. So if we take the solution of e to the power st form, the characteristic equation will become s to the power 4 plus and the solution to this will provide the two omega square values, and those two will be the two natural frequencies. So if we want to solve this, it can be solved. I will not go into the details, I will just give the answer. The two solutions, two natural frequencies, will give the two natural frequencies omega n 1 square, omega n 2 square, and the expressions will be omega n 1 square equal to and omega n 2 square the same quantity. Now, the solution will require the initial conditions. The initial conditions, what we can do, we can provide just a generalized situation. That means at t is equal to 0, x1 is equal to x1 0, x1 dot or the velocity is x1 dot 0, x2 is x2 0, and the velocity x2 dot is x2 dot 0. These are the 4 initial conditions. Then the complete solution can be written. I think it is more of an algebra. So what we will do, I will give the general equation to you in the final form. Now, the reason why I am writing these long expressions to emphasize one point which will be clear at a later time. So this is the solution for x1, and we will get a similar solution for x2. It will be required for us to write that, otherwise the points will not be clear. So these are the general solutions even for a simple case like 2D freedom system, undamped free vibration. Now it is very clear that they are all mixed up. That means two frequencies are involved, omega n1, omega n2, and obviously x1 or x2, none of them are simple harmonic. However, we can see that it is possible to give initial conditions, that is x1 0, x2 0, x1 dot 0, x2 dot 0 in such a manner that the whole system oscillates in a harmonic way. That is, all quantities vary in a simple harmonic manner. What is that condition? Let us see. Say for example, let both x1 dot 0 and x2 dot 0 be equal to 0. That is, there was no initial velocity given. So immediately the sign terms go. Next we give and x1 0 by x2 0 is so all these quantities are known. Omega n2 we have already found out, k2, k1, m1, everything is known. So this quantity is obviously a known quantity. If we keep our initial displacements in this ratio, then what is going to happen? You will find that this term x1 by x2, you will find that this term is going to be 0. And similarly, if we substitute this here, we can easily show, I am avoiding the algebra, that this will be also 0. So therefore, the solution will be then so both x1 and x2 are simple harmonic functions of time with frequency omega n 1. That means it is a natural mode oscillation. But to excite this mode of oscillation, we have to give the initial disturbance like this, and we can show that all along this x1 by x2, this ratio will remain same as this, that is minus k2 by m1 . So whatever ratio I gave, that ratio remains. So if I plot say this is the first block, this is the second block, and displacement is in this direction. So we will find so they vibrate like this. That means always the ratio of the two will be this fixed quantity. That means the shape is given by these two ratios x1. So this is the first mode, and so this is nothing but x1 in the first mode by x2 of the first mode. And this is the first mode shape. The frequency is omega n. In a similar way, we could also excite the second mode. How? There, if x10 by x20 we select as then you will find that this term is 0 and this term will be 0. We can substitute and verify. Then again we are getting same, that means the vibration of the whole system x1 and x2 as functions which will be simply proportional to cosine omega n 2t, and that will be the second mode. I am not writing because these are long, but they will be very similar expressions where this will be cosine omega n 2t, cosine omega n 2t both. and that mode will be again something like this. So, we will see that one goes in this direction, at the same time other goes in this direction. So, mode shape will be something like this, and the extreme positions will, so it will be something like this, all the time they will vibrate. They are in opposite. So, the ratio x1 0 by x2 0 will be a quantity which will be negative in that case, as you can see. Now, why we are studying the normal mode oscillation, we should understand. First of all, this is something which is mathematically tractable, because all the variations are simple harmonic functions of time with same frequency. But we should not also forget the fact that it is always possible to write any kind of displacement pattern of a system in terms of its natural mode. Just like as an arbitrary function can be expressed in the form of a series of simple harmonic functions like a Fourier series, here also it is quite easy to understand that if we give that any kind of oscillation can be always represented by a combination of its natural mode oscillations. So, since a general oscillation can be expressed in terms of the simple harmonic natural mode oscillations, we will investigate only natural mode oscillations. And again, as we have done in case of single degree freedom system, our primary objective will be to find out the natural frequencies, and one extra thing in such cases, we have to also find out the mode shapes. Mode shape means the ratio of the various amplitudes, which will be same as ratio of the various instantaneous values of the coordinates. And as many natural frequencies we will have, so many different ratio combinations we will have, which are nothing but the shapes of the mode. Let us solve a particular example of the case as we discussed, 2 degree of freedom without any damping. What happens when damping is present? Then the various modes which are there in the vibration of the system, the higher modes damp at a faster rate, because they execute larger number of cycles in the same time corresponding to the lower frequency mode. So, therefore, different modes dissipate or they decay at different rates. So, that way the concept of mode itself becomes a very difficult thing to sustain in such situations, and we will ignore damping in all the discussions which we will have. So, it is a system with 2 blocks and 3 springs, they are all identical. This is the first body, this is the second body, and their displacements are represented with the help of x1 and x2. The equations of motion will be derived from the free body diagram. So, this being the free body diagram, both are identical masses. The equations of motion can be written as for the second body, so we can rewrite this simplifying little bit. So, kx2 minus kx1 minus kx1, so it will be plus 2kx1 minus kx2, and this one will be plus 2kx2 minus kx1. Now, the technique of solving this set of homogeneous equations will be that since we are studying only natural mode oscillations, we will assume that both x1 and x2 to be simple harmonic functions of time with the same frequency. So, let x1 be equal to capital X1 cosine omega t and x2 is equal to capital X2 cosine omega t. Now, as we know, in undamped situations, bodies can, their motion can be either in phase or out of phase, and both can be taken care of by algebraic sign of x1 and x2. If they are of same sign, the motions of both the bodies are in phase. If they are opposite sign, then they are in opposite phase or 180 degree phase. Now, if we substitute this in these equations, what we get simply minus omega square m k x1 plus 2 k x1 minus k x2 equal to 0, because cosine omega t everywhere is there and I can take it out. Substituting x2 and x1 in the second equation, or we can write it in this fashion. K minus m k omega square x1 minus k x2 equal to 0 minus k x1 plus so we get, in place of differential equations now, what we have done, we have got a set of algebraic equations that both are homogeneous. So therefore, a solution will exist only when the determinant of the coefficient is 0. And this will give us characteristic equation now. As you can see here, we can solve the whole equation and we can find out the mode shapes. So, directly I can give the solution also. Okay. So, this equation we can definitely solve as this. So, or if we use this plus value, we will get k, m omega square will be k. If we use the minus value, then obviously we will get. So, therefore, the two natural frequencies omega n 1 is equal to k by m, and second natural frequency will be pk by m. So, natural frequencies we have got. Now, after we get the natural frequencies, for each natural frequency, what will be the mode shape? So, if we take this equation for example, this equation, if we substitute the value of omega, we will get the ratio. That means, for the when omega n equal to k by m, say let that be the first mode. So, from this equation we can get x1 in the first mode by x2 in the first mode will be equal to k divided by 2k minus m omega square. Now, this omega square will be k by m. So, it is simply when omega n2 is equal to 3k by m, that is the second mode. Then, if we substitute it here, x1 for the second mode by x2 by the second mode is equal to k by 2k minus m to 3k by m, because omega n2 So, this is simply minus 1. So, second mode shape is the ratio is equal to minus 1, that means they are just equal and opposite. Here they are same, that means they are same. Now, if we plot the situation, how it will look like. This is the first body, this is the second body, and let us plot the longitudinal oscillation in this direction for representation purpose. So, x is not in this direction, but I am plotting the displacement of the mass in this direction, that we have to keep in mind. So, for the first mode, what will be, their amplitudes are same and also in phase. That means, x1 by x2 is always equal. In the second mode, obviously we find if x1 is here, x2 will be equal and opposite. That will be the mode shift. Now remember again that it is only these two bodies are moving like this, because movement is in this direction. So let us try to, this being a very rather fairly simple case, whether it is possible to physically explain the result. So one possible way, let us consider its oscillation, if they oscillate with the same frequency, same phase and same amplitude. What will happen in that case? This spring will have no distortion, because the movement of the two masses are identical at every instant. So distortion being 0, there will be no force. So then it is as good as the spring not being there, and so the system will be equivalent to and their natural frequency obviously is square root of k by m, because this is nothing but two simple spring mass systems of identical nature. The other mode is that they are just equal and opposite. What happens if they are equal and opposite? That means they are moving like this. If they are moving like this, then midpoint of the spring will have no movement. And so therefore, we can consider the spring is halved, and this, there is a wall here, this point is fixed. So it becomes again two systems with this mass, one spring of stiffness k, and this half of the spring stiffness is obviously the double one, because if we make the length of a spring as half, then its stiffness is twice, because two halves of spring, if this is k prime and this is k prime, together in series they should give us k. And you know, when springs are in series, so obviously if k, so therefore k will be equal to, as you can see, k prime, k prime by 2. So when k prime will be therefore 2k. So if this spring length is half, each half will have a stiffness which is double the stiffness of the original spring. So this system is equivalent to now that means total resultant stiffness which the mass has to overcome to move is 3k, and therefore omega n2 is going to be this natural frequency of this system. There is another such system on this side which I have not drawn. That will also have same. So you see that physically also we can explain that there are two situations when the two masses will have same frequency harmonic motion, and how the physical explanation can be given in this particular case. However, this kind of physical insight may not be possible in more complicated situations, and we have to depend on the mathematical results. Now, if there is, but in practice one may say that there is no guarantee that the motion which you will be handling will be a simple natural mode oscillation. But as I mentioned, that a general motion can be represented in terms of natural modes, and we will just look into the matter quickly. Natural or normal mode, whatever you may say. So, if the 2-degree freedom system, there will be two natural modes, and general solution x1t can be written as we know of course that x1 1 by x2 1 is a quantity lambda 1, okay, and mode shape x1 in the second mode will be another quantity. Then of course we can write this in terms of and these two equations are there. So, how many unknown quantities we will be handling? It will be, because these things will be known after solving the natural mode oscillations, this lambda 1 and lambda 2 will be known to us. So, they are not unknown quantities. Unknown quantities will be x21, x22, phi 1 and phi 2. So, therefore, x2 and x1 can be written in terms of these 4 unknown quantities, and these 4 unknown quantities x21, x22, phi 1 and phi 2 can be from initial conditions. There will be 4 initial conditions